Good morning, everyone. Okay, Sherry. Oh, sorry, class 5, right? Yeah, Crystal. Young. Sion. Angelina. October. Wind. Wind. Perry. Harrison. And Lucian is on leave. Logan. Logan. Gary. Ray. Eric. Olivia. Curry. Jason. No, the other Jason. Oh, okay. Aaron. Kratos. You are Kratos, you are not Jason, right? Romeo. Yuri. Johnny. Andy. Trey. Leon. Xenon. Jason. Terry. Link. Marvin. Peter. William. Pauline. Willow. Cindy. Penny. Theo. Liu Wang. Murphy. Sigler. Kerwin. Carl. Tolman Lee. Henry. Zach. He will be here. Colonel. Lucas. Andy. Bob. Scott. Scott is on leave. Ken. Anthony. Maxwell. Charles. Phoenix. Harry. June. David. Okay, good. Oh, yeah, so what's your name? 10? Ziegler, I did. 10. Oh, 5. Sorry. 10. Lugan? Terry. Okay. 510. 10. Okay.
615.
615. Zach?
Yeah.
I did. He told me. Okay. Yeah, okay. So, yeah, how was the exam? How was the exam? Easy? Zenan? Was okay? Exam? Charles? Was easy? Yeah, Charles will always say it's easy, right? And Carl was a little bit worried about the last question, right? The last question, part. Last part. How, right? What happened to how? So, well, the answer was inside the formula sheet. The power remains constant, right? And the reason Carl was asking me, this answer is, this is a normal answer. A good answer would be, remember the formula, power remains constant, so that means the summation of power is equal to 1. That is the right answer. I mean, that is the explained answer. If you just answer, the power remains constant, this is a simple answer. But if you justification. The justification. Remember the okay. Remember Bessel functions properties? There are two properties, right? Bessel functions. There are two properties. One is power. So you just need to say Bessel property number 2. That's it. When you when you go back, check your notes, check the slide. Inside the slide, there is this formula for this power constant. Okay, so yeah, okay, so let's start where we left. So okay, before we start, I want you to make groups of 5 students in each group. Maybe we don't have time for the presentation, but at least you can submit your reports, projects. So if you are working with some professor, right, and you are working in communication systems, right, related to this course, you can have that project. You can choose as a project. Otherwise, you can choose your own project, or maybe I'll try to find out some projects for you guys, and you need to write the report on that. And make sure it is not AI generated report. Make sure of that. Okay. Because we will run it through the plagiarism, anti-plagiarism software. So we'll see. If we have time, we will have presentation. If you don't have time, you need to submit your report. And your exam probably is in 3rd week of June, final exam. 3rd week of June, probably. Right, towards the end of June, we will have final exam. So before final exam, you need to submit your project report. So I want you to make groups, 5 students. And 1 student could be group leader. Who will submit the report? You don't need to submit all of you. Just submit, the group leader will submit the report. Right? For example, those 5 students. So for example, you are the group leader, you will just submit the report. But on behalf of all. Okay? I will post it this weekend. I will post it how you write the report. Maximum 5 pages. Not more than 5 pages. 5 pages is enough. 4 pages okay, 3 pages okay, with the simulation results. With the simulation results. Total 4 or 5 pages, maximum. Okay? Because that is part of your grade. 15% of your grade is project. Okay? So normally every student gets 14 normally. And a very good student gets 15 out of 15. Okay. So we'll see if we have time, we'll do the presentation, otherwise just the project report simulation, and I'll post it on this weekend. Okay, so let's start. I think long time ago, right? Our lecture was long time ago. Anyhow, so let's start. I think we were here. Okay. So it's not working here. Random process, right? What is a random process? And what is a random variable? Well, we talked about random variable a lot. If you throw a coin, right? What is the outcome? Well, we don't know, right? It may be head, it may be tail. Now, what is the process here? Right? A random variable assign 1 or more numbers to each outcome, all right, of a random experiment. This is random variable. It assign a number on a real line, right? Positive number. 1, 2, 3, 4, 5. This is random variable. Whereas random process, what is that? Every such outcome is assigned a waveform. A waveform. Whatever the outcome comes, right? That outcome is assigned a waveform. And you can, if there is x, right? Bold x, you will say it is a random variable. If it is x of t, x inside t, you will say it is a random process. Like here, so if we write x of t, this is random process. If I say x, then it's a random variable. Right? So this is why the definition says it assigns every outcome a waveform. And when we talk about the waveform, right, we talk about the time, because how you draw waveform, right? me on my x-axis, time, right? Let's say it's voltage or current, right? So I assign, well, so this is a waveform, right? So waveforms are drawn like time on the horizontal, right? Time on the horizontal axis or x-axis. So similarly here we are drawing, right, a waveform. It's called, right, this xt here. So for example, here this is my sample space, right? This is my sample space. Inside I have those number of outcomes. Every outcome, I assign here a waveform. This is called random process. This is called the random process. So here, see here, this is assigned a waveform here. So here, this is assigned a waveform. This one, I mean, all the samples, all those outcomes, they are assigned a waveform, right? And when I collect all of those, right? If I collect all of those, it's called ensemble. Collection of all the waveform is called random process. The collection of, see here, all this collection, it is called this random process, right? See here, it is random process. Get it? Right? So, the randomness is associated with the occurrence of a particular outcome, which in turn determine the sample function observed. So these are sample functions, right? These are sample functions, right, against the time. So when we write random process, so we denote it like x of t. So what we do, we remove this, right? We just write out x of t. This is random process. So now here are some random processes. Gaussian random process. So you can see this is sample space, right? T1. So it's x T1, number 1, number 2, number 3, number 4, and so on. Similarly, sample function of Poisson process. This is that Poisson process. See, this is time, and this is that sample here. This is that waveform, right? This is that waveform. This one. Similarly, this is the this one is digital binary, right? Digital, and this is the sample. So these are the random process, different random process. Now, a random process is described by its ensemble of sample function and PDF over the ensemble. Ensemble means collection of waveform. Collection of waveform. Each time we perform the random experiment, a number x t1 is observed at t is equal to t1, right? So each time we perform an experiment, you see here, this one, right? When we perform an experiment, we observe. Then second one, we observe the second, and the third one, we observe the third one. So and go on. So that's what it means, right? Each time we perform the random experiment, a number is observed at t1, depending upon the particular outcome and the corresponding realization, right? Corresponding realization is this. This is realization, right? So here, the amplitude of the sample function at any fixed instant t1 therefore represents the random variable x t1. So the amplitude will represent the random variable. It is a random variable. Basically, collection of random variable is a random process, right? That's what it means. We will use the notation x1 to represent the random variable at instant t1. x1, which means I'm talking about t1. x2, I'm talking about second time t2. x3, and so on, right? A random process can therefore be viewed as a collection of an infinite number of random variables. So, what is, in simple words, a random process is a collection of infinite random variables. That is what, I mean, simple definition is that. The random collection of infinite number of random variables. And of course, when we talk about random process or random variable, we talk about the for random variable, we also talk about the PDF, right? also have here we also have here the expected value or the mean value, the average value. Similarly, we also have the here mean square value. So here the expected value. That's how we write different, right? That's how we write it differently. M of x or x bar or expected value of x. It is basically x times the period, right? X times the period. And what about the mean square value? Well, mean square value is expected value for x squared. That is what the mean square value, right? So x squared times f of x dx, x squared times the period, right? What is the autocorrelation function? Well, this is the autocorrelation function, same as for the random variable. We are also having this autocorrelation function, right? Rx. What is that? It's a measure of correlation between sample function values of the random process at T1 and T2, right? That's what the autocorrelation function is. Then the autocovariance function, what is that autocovariance function? Well, this is autocovariance, C of x, that is equal to the autocorrelation function minus the mean value or the expected value of at T1 and the expected value at T2. This is the autocovariance. What about the variance? Well, variance is here, right? Variance is basically the autocorrelation. Then the correlation coefficient, well, same as, right? Now we are talking about random process. So here is the correlation coefficient. Well, now what is a wide sense stationary process? A wide sense stationary process is one which obeys those two rules, right? Which obeys those two properties or two rules, which is that for a process to be wide sense stationary, and when we say wide sense stationary, well, there are two. One we call strict sense stationary, and one we call wide sense stationary. Strict stationary process is one whose properties do not change with time. Whose properties do not change with time. We call it strict sense stationary process. And what is a wide sense stationary process? So here is the wide sense. If the expected value is constant, right? And then if its autocorrelation function is basically equal to this autocorrelation function is R of x tau. So for a random process to be wide sense stationary, we only require that mean is constant and the autocorrelation function depends only on the time difference, this tau. Tau is T1 minus T2. Right. That is what the for a wide sense stationary process, to be a wide sense stationary process, it has to follow those two properties. And here is the what is an ergodic process? Here a random process is ergodic if all time averages of sample function equal corresponding in sample average. And since time averages by definition are independent of time variable, it follows that the ergodic process is always stationary. So here we have random process, then we have wide sense, then we have stationary, then we have the ergodic process. So what is an ergodic process, or what is that time average, and what is that time average, and what is the ensemble average? So here, if we define time average, time average is basically, remember, x sub t, this is your time average. This is equal to limit t goes to in sample average, and one is the time average. So when you well, you are talking about the expected value, right? X times f of x. So this is the difference between in sample and time. Then cross-correlation function. Well, cross-correlation function, it provides a measure of correlation between two sample functions. Functions, amplitude of processes x and y. Cross-correlation, right? Cross-correlation. What is that? Cross-correlation between x and y. That is equal to the expected value of x and y. And x is at t1, y is at t2. The random process, x and y are said to be uncorrelated if they have this property, which means expected value of x of t times the expected value of t plus tau. Tau is that time difference. If they are orthogonal means there is no relationship between x and y, then this rxy tau is zero. If there is no relationship between them, if they are independent from each other. If they are independent, that's how. That means they are orthogonal. So it is equal to 0. Note that if either xt and yt has a zero mean, uncorrelatedness means orthogonality and vice versa. Now x and y are said to be independent random process if the set of random variable is statistically independent of the set of those random variables y1, y2, y3, right? They are statistically independent, x and y, right? If the set of random variable, let's say x at t1, x at t2, x at t3, and so on, and set of y t1, t2, they are independent, right? So they are statistically independent. Independence implies that the joint PDF of the random variable is the product of the PDF of their individual variable. The random process x and y are jointly stationary in wide sense if x of t is if x of t the random processes x and y are jointly stationary in one sense if x is WSS, y is WSS. X is wide sense stationary, y is also wide sense stationary, and their cross correlation is invariant under the shift of time origin. That is, their autocorrelation function is basically equal to Rx tau, where tau is the time difference. Gaussian random process. A random process x of t is said to be Gaussian process if the random variable x1, x2, x3 are jointly Gaussian for n and for any choice of t1, t2, t3. Many processes that arise from natural phenomena are approximated well by Gaussian process. Right? In nature, most of the natural phenomena they follow Gaussian process. Using the central limit theorem argument. Example, what are the examples? Example is the noise, right? Noise in resistor and diffusion, noise in semiconductors. Gaussian processes are also relatively easy to handle analytically. That's why they are so important in communication and control systems. Important properties of the Gaussian processes. Here is mean a Gaussian process is completely specified by the set of means mi is equal to expected value of x of ti, and the set of autocorrelation function, right? This is the set of autocorrelation function rx ti tj is equal to the expected value of x at I and x at j, where I and j they are not related, right? They are not related. They are not equal. For a Gaussian random process, x1, x2, x3, for any set of distinct time instants are correlated, then they are statistically independent. If they are um, uncorrelated, they are statistically independent. Right. If x of t is a Gaussian White-sense stationary process, then x of t is a strictly stationary Gaussian process. For an LTI system with a Gaussian input process, the output is also Gaussian, right? If input is Gaussian for an LTI system, if an input is Gaussian, the output is also Gaussian, right? The output is also Gaussian. Moreover, x and y are jointly Gaussian. X and y are jointly Gaussian. Well, power spectral density, we know in chapter 2, we already done that power spectral density. So here is the definition for the power spectral density. G of x is equal to limit t goes to 0, this x t f squared divided by t. We already defined that. For each sample function, we can write its PS, well, this was the PSD general formula, right, in chapter 2. But now let's apply it to the random process. So if we apply it to the random process, this is how we can write the PSD, power spectral density of the random process, right? So here is that. So here is the process. Here is that general definition, where this xt fi is the Fourier transform of the truncated sample function x t this, right? A meaningful definition of the PSD of a random process would be the ensemble average of PSD of all sample function. We already defined the ensemble, right? We already defined the ensemble. So here, we are talking about this ensemble, right? We are talking about this ensemble average. Here, this is the PSD of a random process. Now, power spectral density of a random process. Continue. The PSD describes power distribution of a random signal as a function of frequency, right? As a function of frequency. Power distribution, right? How power is distributed. For a WSSS random process, the PSD is the Fourier transform of its autocorrelation function. We already done that. For a WSS random process, PSD is the Fourier transform of the autocorrelation function, right? So if you take the Fourier transform of the autocorrelation function, it's called linear Singh theorem. Similarly, what is the autocorrelation function? If you take the inverse Fourier transform of this, you get the G of x. Inverse Fourier transform of G of x, you get the autocorrelation function. It follows that this x square of t is equal to r of 0, right? If we put here right, if we put here if we put this right, if we put half t is 0 here, we get g of x, g of f, d of f. If we put tau here, right? If we put tau here, 0, right? So we will get this definition. So that is area under g of x represent the total power of the random process. So now this is the power, right? Total power of the random process. Now, response of an LTI linear system to random signal, right? The output of an LTI system with impulse response function to the White-sense stationary random is given as this, right? So we have a LTI system, x output. So, well, we had the power spectral density here, G of x. Similarly, output, we have the power spectral density output. And then we have this h of t is the impulse response, and capital H of f is the Fourier, well, it's the transfer function of this system, this LTI system. So we can write, well, the output y of t, it is a convolution, we know that. So it's a convolution here from, we can also write x convolution to h or area. The PSD of the process y, PSD of the output y is equal to h of f, the transfer function squared times g of x. We have done that in chapter 2. So here is that, right? Now apply inverse to both sides. If we apply inverse Fourier transform, so what we get the autocorrelation function is equal to the h of tau convolved with h of minus tau convolution with the autocorrelation function of x. Now here, what is a white Gaussian noise, right? So yeah, so white Gaussian noise. Why it's called white? Why it's called white? White Gaussian noise. Why it's called white? What's a white color? White color. Why it's called white? What's the reason? Why it's called white? Yeah. Why it's called white? White color, right? It is, we call it white. So what's the property of white color? Well, white. It contains all the visible frequencies, right? It contains all the visible frequencies. See here, it contains all the frequencies. That's why it's called white. Just like white color, it contains 7 colors, right? White color consists of 7 colors. Am I right? And all have equal proportion. All have equal. That's why we see it as white. It contains all the frequencies in same quantity. So that's why it's called white, right? And it's a Gaussian process, so we call it white Gaussian, right? White Gaussian noise. The term white noise is used to describe a white sun stationary random process whose power spectral density is flat over the entire frequency band. This is the spectrum of the white Gaussian noise. It is flat, right? It is flat, and here, and this is the N is the noise PSD. This is the PSD, right? This is the noise PSD. NO is the noise PSD, and NO, if you remember, I don't know if you've done this or no. This NO, this is equal to KT, right? What is K? K is remember Boltzmann constant in your physics. Boltzmann constant. Right. Remember Boltzmann constant in your physics, high school? K, and T is the temperature. Boltzmann constant, how much is the value of this? Boltzmann constant, how much is the value? 1.28 times 10 to the power of minus 23 joule per Kelvin. Right, per Kelvin. This is the Boltzmann constant, and similarly T is the temperature, right? So here, if I take the, well, this is the inverse Fourier transform, right? So similarly here, I can get this, right? I can get this if I take the inverse Fourier transform of this. I will get this, right? So PSD and the PSD and the autocorrelation function, they are Fourier transform here, right? Autocorrelation function and PSD, they are um, Fourier transform pair. So if you take the inverse Fourier transform of this, what you will get? You will get a spike, right? A spike. This one. So here, what is G of n? Well, this is the for white. This is n O divided by 2. Taking the inverse Fourier transform, right? So if you take the inverse Fourier transform of that, what you get? You get autocorrelation, right? White noise represents the ultimate in randomness in that equation, since this equation implies instantaneous decorrelation. That is, any two samples of WGN are uncorrelated no matter how closely spaced they are. They are uncorrelated, right? So that means noise is uncorrelated, highly uncorrelated at any two different time instants. Noise is uncorrelated at any two different times. Right, that's what it is. White Gaussian noise that are also Gaussian are called white Gaussian noise. White noise processes that are also Gaussian are called white Gaussian noise, WGN. The samples of WGN, N1, N2, and 3 for any set of distinct time instants are jointly Gaussian random variable. It follows from equation, the star equation, that the Gaussian property that they are statistically independent. They are statistically independent. Now, WGN is an idealization of noise observed in electronic components. The noise is caused by the chaotic motion of electrons in these components and commonly referred to as thermal noise. Right. This is the definition of a thermal noise. When an electron moves chaotically means here and there, right? Follow any direction. So they generate heat. Right. So it is called the thermal noise. Since the random motion of a large number of electrons contribute to this noise, we can apply the central limit theorem to conclude that noise is a Gaussian random process. Right. Since the random motion of a large number of electrons contributes to noise, we can apply central limit theorem. And when we apply central limit theorem, CLT, we can say that noise is a Gaussian random process. Okay. Experiments conducted by John and Nyquist in the 20s showed that the power spectral density of a thermal noise was constant for a frequency as high as 100 gigahertz. Right. Although WGN is useful mathematical abstraction, it does not conform to any random signal or noise observed in real life. Why? Because of this. From minus in noise, well, this is infinity. So WGN has infinite average power, which is physically impossible. So here, if WGN is passed through a non-ideal filter with a transfer function of passed through a non-ideal filter with transfer function h of f, the output noise spectral density is given by here. G of y, we are passing it through a non-ideal filter. So this is how the power spectral density y output is this. The mean square output power is given by here, what a mean square power, right? So that's how you define mean square power, which is basically the output, or which is basically the power spectral density of the output times integrate that, right? So if we plug in the values, we get n times h of f of 2 here. Now here, if you notice here, we have minus infinity to infinity. Here we start from 0 to infinity. Why? Right? Here infinity, right? And then we are equating it to from 0 to infinity. What's the reason? What's the reason? Right? What's the reason? Here it's from minus infinity to infinity, but here we are putting it from 0 to infinity. The reason is yeah. What's the reason? Sonu? What's the reason? What's going to be the reason? Well, the magnitude response is an even function, right? Even function. So what is an even function? Remember even function definition, right? So it's an even function, right? So we can, instead of writing from minus infinity to infinity, since it is even function, right here and here both same, so that's why we are writing, it's easy to write like from 0 to infinity, because this magnitude, this response is even, right? So I can write from 0 to infinity, that's why it is like, okay. So I have to put, well, if it's an even function, right? So I need to write 2 here, right? So that 2 will cancel with this 2. That 2 will, well, it's an even function, right? So I can write it, well, both are equal, so I can double it, right? I can write it 2 times. So here I will write 2, here I will multiply with 2. When I start from 0 to infinity, I will multiply this with 2, right? So that 2, this 2 cancel out, and we get the, we get this. So now here, if we have an ideal filter with bandwidth Dn and gain equal to the maximum gain of the non-ideal filter, as shown in figure here, as shown in this figure, here, as shown in this figure, right? This is Dn, and this is also even. So here, then we can write down the mean square output power is equal to n times 2 divided, n O divided by 2 times Dn h of f, and that is also equal to n, right? That is also equal to n En h of f square, h of f square. And here is that filter. This is ideal filter. What is noise equivalent? What is noise equivalent? Yes. Class you are in? When? When you were absent last class?